Hello there, welcome to this video. We're going to pick up where we left off with creating discrete event simulations with the Ciw package. So last time we wrote out this little simulation. We set a seed number, we defined a network that was defined by a set of arrival distributions, one for each node. In this example, there was only one node, and one service distribution and some number of servers. It's kind of, I think, close to the most basic that you can do. And I can't remember if we talked about it, but there's this Kendall's notation, which we will come back to another time. But this is M for the arrivals being memoryless, and M for the service distribution being memoryless, and C being the number of servers. So in this case, we could say this was an MM3. It's one of the simpler models, and we'll come back to that notation another time. So we then defined initialized a simulation object, and then we ran the simulation for 1440 units of time. So the next part of the official Ciw documentation gets us into some topics around the seed numbers and also around initialization and finishing off the simulation. So the first thing that maybe we'll think about a bit here is the idea of doing multiple trials with different seed numbers. So while it is the case that we can control the pseudo-random number generator's behavior by setting the seed, we're kind of interested in the fact that there should be some overall probability distribution of outcomes that, yes, running this seed will produce the same results, but really the seed is a kind of arbitrary number, and that what we're hoping for is that our simulation results are exchangeable or identical in distribution, hopefully, with the true data generating process for something that we're modeling. So we want to actually run this on multiple seeds to produce a distribution of results of some kind. So let's start taking away some of these little pieces here. And for the example that's in the documentation, they look at average wait time. So we'll go average waits. We'll just create a little list there. And then we're going to create a collection of trials. So we could create a for loop for trial in some range, which is really just going to specify a sequence of integers for us. And we'll go 10. So 10 integers. And we can nest that inside of the for loop so that for every iteration, we're going to create a separate simulation object. And we can reuse this network object. And that's one of the nice things about separating these two steps is we define the simulation network, but the simulation itself can take in the network, the same network class, so we don't have to redefine the whole network every time. Hopefully the gist of that made sense. And then we can set the seed inside of this loop for every one of our trials. So here our trial, and really I'm going to deviate from the documentation that calls these trials, although I get it, but maybe we should say for seed in, or maybe even more descriptive is trial seed. And we will go trial seed so that we're setting a sequence of seeds of 0, 1, 2, 3, 4, all the way up until and including 9. Okay, and then we can define our simulation object. We already kind of kept that from last time, and we're going to run the simulation. Now, there's a couple more things that the documentation wants to emphasize here, which I think are pretty good points. So when we set up our simulation object, it is taking this network, and it is assuming that there are no customers at any of the nodes. The whole system starts off empty, which may not be a realistic situation. And so you may want to run the simulation for long enough that you have kind of filled it up to what's going to be approximately an equilibrium state. That the idea of this system is that there's some long-term equilibrium where the details of the state will change, but eventually you get this convergence in distribution for how the system behaves. So in order to get that, we might want something like a warm-up time. I don't know what we should really pick. I'm going to deviate from the docs, but basically show you the same idea. So we'll call this warm-up time, and let's say that this is 100. And then maybe we'll say that we want, let's say a cooldown. And why would we want a cooldown? So the warm-up, the reason for the warm-up is so that we get something hopefully that's kind of equilibrated a bit. And the cooldown actually has to do with a kind of statistical censoring, that depending on what question you're trying to ask, you can get in statistics this problem of censoring. There's different ways of dealing with censoring. One is to statistically model using probability distributions. But in this kind of pure simulation approach, it's pretty common to have a cooldown, which really just means running the simulation for even longer, just to make sure that for the interval of time that you cared about, that you flushed out all of the customers that would have been relevant to the system over the interval of time that you care about. Here we're going to set it to 1,000, and then maybe just to break something down further, I don't know if I would really call this target time in general, but let's just take that 1400 there, and so we'll call this simulation time or something like that. And we will just take the sum of these. So warm-up time plus the target time plus the cooldown time. And we'll put that right in there. There's our simulation time. Now, there's some other things that maybe we want to calculate. Like I alluded to this here by having the average weights. We actually need to extract the results that we're interested in after the simulation has run, right? So let's get our records. And our records, we can use the get all records function that we looked at in a previous video. And then we can get the weights using a list comprehension. So we might go record dot waiting time for record in records if record arrival date was, let's say, strictly later than the warm-up time, so we're not going to grab results from what was too early, and that our record arrival date was also less than, I guess this would be, we would take the, well, there's probably different ways that we could write this, but let's just take the simulation time minus the, yeah, we could take minus the cooldown time. I mean, it's really just an additive complement type of thing here. Now, this list comprehension's gotten a little long, so let's break this into multiple lines just for a little bit more readability here. Get down into some of those different cases. So, assuming I don't have any bugs there, we've got our weights, and the next thing is, you know what, in the documentation example they use Ciw Python, they could take the sums divided by the length of the weights. Because NumPy is already a dependency, it's actually quite tempting to just, as a dependency of Q, it's actually quite tempting to just use NumPy. Like, I'm actually not sure why you wouldn't, if your package depends on it. But whichever is fine. So we'll take the mean of the weights, mean weight, and then this average weights plural will append our mean weight to that. Now let's just actually double check that we haven't broken anything by attempting to run the file. It actually runs, and runs quite quickly, which is, I never complain about that. So we could also take a quick look at printing our average weights. There they are, collection of floats. And so you can see even a quick rough sense of the scale of 3, 4, 4-ish. I mean, I'm being very rounding to the first decimal place, but you know, you get the sense of here. Maybe on the low end, one of them was a little bit less than 3. And let's see, I also see there was one that was greater than 5, I think. Yeah, there's a couple of them that are greater than 5. So that's fair enough. Now, we might also take an average of the averages if we wish. So we can go np mean and in this case it's 5.626, etc. So on average it's actually greater than 5, which surprises me, but It's totally fine. Oh, actually, it doesn't surprise me anymore. Okay, now the last thing I see here is they say, for the final example using Ciw, we have found that on average customers wait 5.62 minutes. That's what we just calculated. What would happen if we added an extra server? And so they ask, what if we repeat the analysis with 4 servers? Okay, great. Well, that's an easy change. That's an easy code change for us to make. So let's hop up to, what is that? 7 here. I just realized for my NeoVim, I should turn on the relative line numbers. Like, what the heck? What am I doing? I'll fix that later, though. Okay, so increasing the number of servers decreased the waiting times down to 0.79. A little bit of a sanity check. We know that from statistics, it doesn't necessarily have to go down, but that is what we kind of expect on the average. And lo and behold, it's slightly less. So this is kind of your first example following these tutorials of dealing with, just to review the concepts, we had warm up. And the reason why we did that was to make sure that we've run the simulation long enough to get into equilibrium. It's really one of those parameters you can spend time tweaking to go, have I run it long enough? And one of the things I didn't cover here is sometimes you might actually want to do some coding to set up your simulation to be in a specific state, like taking the current business state if you work for a business or of an organization that's like a government organization or whatever. So warm-up's one of the ways of just saying, can I start off in statistical equilibrium, roughly? The target time is how much time you really were interested in simulating for. The cooldown time is really just to say we keep running it longer to make sure we've kind of flushed out the system for any of the customers that were of interest during the target time. And then we wanted to collect the statistic, and how you can gather up multiple iterations of a statistic is to run multiple trials, controlling the seed number each step of the way. Initialize a simulation object that takes in our network, which thanks to this particular API, we can reuse the same network class over and over again, which is nice. And then we do the simulation for a total amount of simulation time that includes the warm-up, the target time, and the cooldown. Then we grab all of the records and we calculate what we wanted to know from the record. So in this case, the waiting times from each record. And we're trying to get stuff that happened later than the warm-up time and before the cooldown time. Really, the other way we could calculate the simulation minus cooldown is to take warm-up time plus target time, but that's fine. And then for each of the collection of weights, we calculate the mean for that particular trial, and then we gather up and append to a growing list the average weights across trials. And here we just printed the result, but of course, if you're doing some more involved stuff with a pipeline, you might want to save these results somewhere or produce a dashboard or all kinds of things. So with that, I hope that you got some value out of that video in terms of seeing how you can do some repeated simulations and try to make the simulations a bit more generalizable or match at least the idealized situation that you're trying to model. And we'll catch you in the next video. Have a great day.